for track 2, if you still want to work on Lab 14, you really don't. I mean, it's because we are running out of time, right? So I just keeping all these essential questions for you guys. And I just did Lab 14 and 15 last week. It turns out it's super simple. So I think it's very doable for you guys. Just get it done within 1 week. All right. Why we want to do it within 1 week? It's because for track 1, you need to understand how to use it, so you can spend the time for the rest of the week to work on your project, right? Make sense? I don't want you guys spend like so much time to work on the questions and calculations, which is not super essential for the project. So as long as you know how to make it work, it's okay. So I'm combining Lab 14 and 15, but still there will be 2 assignments to submit. Let's take a look at that really quick. So Lab 14 in lab, only 2 questions. Okay, doable. So eventually, what you are going to do is just look at the website. I think it's over here. All right, so there's a picture. I also have this picture on my website as well. So look at the picture, look at the parts, what they look like, and put it on the board and solder it. Okay? I recorded video. Let me show you. Yeah, I think I have all these essential information on my website, can help you out. Okay, so that's the board I soldered, and I didn't even use a hot plate since I can't. I just don't. I don't have to. Sometimes if I have like hundreds of components on the board, I probably will use a hot plate. Otherwise, it's faster to just use a soldering iron for me. Okay, just let you guys know. You can use that iron as well, but you can see these are pretty much just repeating parts. Yeah, some tips you need to know, otherwise you're making mistakes, all right? So these are just repeating components. Usually 2.2K can read it. You can read from it. Super simple. And the LEDs, pay attention to that green line. You probably couldn't see it. Can see it a little bit? So there's a green line. That's cathode. Make sure the polarity is right when you solder it, okay? So the green line is a cathode. So keep the green line. Sometimes this LED in the middle is a black line instead of a green line. But anyway, so whenever you see a bar on the top, that indicates a cathode of the LED. A bar, right? So the cathode of the LED has a bar on it. So these are just resistors, just repeating, super simple. So the way you want to do that is, because this board is so small, it doesn't have many components on it. So the way you want to do it is you grab an empty board and use a flux, the syringe. I probably will have to order more of the flux. Use a flux and place the flux onto the pads first to make it sticky. Then you probably reach out to the TA. I may have to put all the components in the boxes, and you find the boxes and place the components in the tweezer and place them on the pads. Because the flux is very sticky, so it's going to hold the parts onto the board, right? So you can get all the parts placed on the board and then solder them at once. Okay. If you are using the hot plate, you probably want to use flux and the solder paste at the same time to make it sticky. So you can place the parts onto the pads, and then place the board onto the hot plate. But the thing is, even though just for one section, it's still 20 something students, will be 10 groups. But there are only like 2 hot plates, I think, 2 or 1, I don't know, maybe 2. One hot plate and 1 oven. Yeah. Yeah, so I'll be there for, let me see. It's the first section. I'll teach you how to use a soldering iron to solder it. Okay. Probably record a video or something. So one thing you need to know, on Dr. Carlson's website, he asks you guys directly solder this guy to the board. Okay, so this is the MPU. And make sure it's the right angle here. Even though mine is not perfectly a right angle anyway, close. So he was asking you guys to directly solder this to the board. But the thing is, if this is a faulty module, then you have to destroy from the bottom. And I have a way to do it, but you probably don't know how to do it. It's getting challenging, you know what I mean? If you directly solder this guy, to this daughter board, how to get rid of it if you see issues. The iron tip only has one tip, right? Every time you can only heat up one joint. So you have to move your finger like at the speed of light. Okay. The hot gun, yeah, you can use the hot air to blow to the joints, but these are plastic. They'll melt. Okay, in front of the hot air blower, so that won't work. What else you can do? You know, you can heat up every single one, because these plastic holders are not holding these pins really tight. You heat up here and you push it, so you can use the tweezer or plier to remove every single one, like pulling them out. That also works, but still it takes a lot of time. So the best way to do that is just solder a header on it, female header on it, and then just plug in, right? So if this one is broken or getting damaged, you can replace with another one easily. So you don't have to unsolder it from the board. Does that make sense? So always have a socket for the modules like this. Right? Okay, so at the bottom, it could be confusing, but I took pictures of the bottom of the board and post on my website to explain. I also record a video to make it clear, because following his tutorial, I didn't notice that we need this guy, but eventually I figured out why. Did you see that this is it's called a shield, right? It's a shield board. Shield means you plug in on top of something, a CPU board. So it's providing some peripherals. And definitely these are easy to understand because these are just female header pins, just making connections, right? So these connections are wiring these pin signal to the top through the board over here. Okay, we are not designing the PCB, so it shouldn't be difficult to understand. But what is this guy doing?
It's jumping LPF or 5 volt to.
Yeah, see, you just have to do that as well. So that's the 5 volts from the USB. Let's look at the schematic. Did you do that, Cover?
What?
Did you do this little 5 volts?
Yeah.
You did that? Cool. Schematic. Okay, so it is this guy. So this is on the pig board, right? It's on the pig board. What is this doing? Take a look. V bus, digital plus, digital minus. We don't know what the signals are, but we know that these are signals, right? We have a ground, we have V bus. So V bus is 5 volts. Remember, USB is always providing 5 volts. Okay, doesn't matter what type of connector that is. It's 5 volts for USB. So 5 volts comes in. So definitely this header has 5 volts, right? Okay.
And
so
if you don't have it there, it's just a voltage divider over the 2.2 resistor, or?
I think it's trying to boost the voltage to some sort, but if you have a 2.2 resistor, it's not making too much difference, right? I mean, we are not considering why he has this 2.2 resistor crossing these 5 volts. Sometimes we put a jumper header onto the top, sometimes we don't, but is there a difference in terms of power delivery? You know, the difference is only like it's dropping some voltage to the 2.2 ohm resistor or not. Otherwise, what's the difference? It's 5 volts comes in, right? You put a jumper here, it's directly connecting 5 volts from here to here, and then to the fuse, and then providing voltage to here, and which supplies 3.0 volts VCC for everything, right? Otherwise, it's just if you don't put a jumper here, it's just dropping some extra voltage across the 2.2 ohm resistor, or you can say it's limiting the current or whatever. I don't know. I'm not getting the point actually. It's not a huge difference. But I think the intention by reading whatever the Dr. Carlson's tutorial is, if you put a jumper here, it's providing more current to the circuit, which makes sense, a little bit more, yes, because you don't have this 2.2 ohm resistor limiting the current, but it's such a small resistance. It's almost zero. It's not making a big difference anyway. So let's ignore that, okay? Let's ignore that for now. So it's basically just 5 volts. Doesn't matter if it has a resistor or just a jumper, doesn't matter, just 5 volts, okay? Make sense? Just 5 volts. So this 5 volts on the board is this guy, right? This guy. Okay, so that's the header. And if you look at this board, schematic of this board, yeah, I think this explains everything. Let me see which one I'd like you guys to look at. It's better to start from the first one. I only have 4 snapshots to explain what's really going on, okay? So for this board, you want to, eventually, this should be able to power up by USB. So eventually, if you plug in USB here, VCC will be delivered to the board. From where? That's the question. Let's take a look. Okay, take a look at it for a few seconds. Power supply is always the first thing when you build a system. First ever. Okay? Here's a switch on the board. Here. Determine, like, if you want to charge up the battery is over here. And plug in. Oh, it's not working. Why? Because I switched this one to charging. Okay, this is a charging chip which is able to regulate the voltage and manage the charging current to this battery. So where's the power source to charge it up though? Do we need another plug or like jack power header connect to the wall or something?
From the pickboard?
From the pickboard, from the USB, right? Make sense?
Yeah.
So USB providing 5 volts to where? To here. So whenever it's switched to the left, it's charging. So we want to use that 5 volts to charge up the battery through this charging chip. Okay, so if I switch to the middle, which is off, right? Should be off. If I switch to the right, you see it's on, okay? So now it's using the battery's voltage to power up everything. The green LED is on, this LED is on, so which means it's powered up. It's also powered up. Make sense? So we have to look at the circuit to figure out how this works. Okay, how this works. But you see there's nothing connected to it, but it's still working because the battery is charging, the battery is powering up everything, okay? All right. Now let's come back to this one, the first one. So there are several options, several combinations. USB and switch and battery, okay? So USB on or not. So plug in USB or not. Battery charging or not. See how that works. Okay, 4 options. So totally giving you 4 different combinations. First one. So this is the header. So the schematic over here is a schematic of this daughter board. Okay, just let you know, it's not a pig board, guys. And that's a connector connected to the battery. The connected to the battery. So plus and negative, 2 terminals of the battery, right? What about VCC? So we got a VCC on the board of the shield board, right? So what is this one doing here? VCC. JP2. What is JP2 here? Anyway, probably it's this is a regulator. This is a charging chip, but it's not being used. Wait, let me see. Oh, this is the charging chip. This is a charging chip. This is a regulator not being used. I didn't even solder it to the board. Take a look. So keep in mind, I'm recording this video, but keep in mind, this is nothing to be soldered to this spot. Okay. If I plug in VCC, and I'm labeling that this is from the PIC, how that works?
One of the pins on the pick.
Yeah, at the bottom.
Yeah.
See? You got every single pin from the PIC connect to this daughter board. So there will be one of them must be VCC. Okay. So VCC is here. So if you have VCC, so everything is powered up if I plug this in, right? Make sense? So now let's see the first case. USB VCC no battery. So USB connected, connect to the USB. So which means if you connect the bottom board to USB, so VCC will be available, right? If you don't connect the USB of the PIC to the computer, there's no even VCC, even though there's a VCC pin, but there's no voltage. Make sense? Okay. So if you connect USB, VCC will be available, but no battery. Would that work? Yes. Why? Because you have VCC, right? Now let's see. VCC is also shorted to here. So if they have the same name, means they are physically shorted on the board. So VCC here, that's a low pass filter, just stabilizing that power supply without any ripples. And what else? What about this guy? Where? This guy. That's something we care about. This is the accelerometer, right? It's the MPU module. Is there a VCC on it? Yeah, so it's powered up. Okay. So what else do we know? Do we need? No battery connection. No battery connection. So the goal is to collect some sample, right, from the accelerometer and the gyroscope, which is the module on the top. So the question, really quick question is, would this work? Only USB plugged in to the bottom board and no battery. And I switch the top. Doesn't matter because battery is not even working. It's not charging or not discharging.
Yeah.
Can I collect data from this guy?
Yeah.
Yes. VCC is on. Ground is shorted to the common ground. It's gonna work.
Yeah.
Okay. So where's the data is sent? Where do you send the data to the PIC? To the module pins, RC3 and RC4. So these are I2C pins. Okay. I2C pins, we don't need to worry about it because they are basically just two digital pins, RC3, RC4. So for IC2 communication, the protocol is more complicated than SPI, but it's slower. It's only taking 2 pins. So it's taking less pin resource of the chip. So there are only 2 pins, SCL and SDA. It's easier to understand because CL means clock, DA means data. It's only 2 pins, clock and data. Okay? We don't want to dig too deep into it. It's just need to know two data pins, 1 clock, one data, digital pins, and power supply and ground. That's it. 4 pins for I2C. All right. So if you power it up through VCC, it's getting powered up. It's going to send signals through these 2 signals, I2C, to a PIC at the bottom, and eventually PIC will receive the data through I2C and send it to the POTI. That's how that works. Okay, or SD card, doesn't matter, depending on where you want to store the data. So first type of configuration works, right? No problem. Second, USB, which provide VCC, okay, through the PIC, and battery, and then you switch it to charging. What's really happening if you do this?
You're just showing it to charge the battery.
Yeah, so the switch over here, right? You are charging. Battery is over here, connect to the battery. Okay? If you switch to charging, where is really charging up the battery and how? VCC is still available, right? Because I turn on the USB and VCC is plugged in, so VCC will be available here. 3.0 volts. Okay, so this VCC connect to this VCC because they are all called VCC, connect to this VCC as well. Okay? Then how do you charge up the battery though? Because here's the battery, negative, positive. So positive, negative, so basically these 2 wires are shorted to these 2 lines. And this connector, we don't have to worry about it because this is ground. See, there's a little wire here, but there's disconnected. So basically ground is shorted to the negative. Makes sense? You want a negative pin of the cathode of the battery to be the common ground, so 0 volts as the baseline. Okay? So positive goes to here, shorted to this line, comes to here, this switch, the switch I showed you guys just now. Okay? And if I put it to charging, so it's actually this wire, the positive pin of the battery will be connected to the charging wire here, and the charging wire here is shorted to the charging chip, output. Okay. Any questions by far? Is that too fast? What's the question?
What's the necessity for the 2 connectors then in the that we were just talking about? Like,
You mean here?
yeah,
Uh-huh.
because like it seems like one could just be kind of permanently shorted to ground. And the
Yeah,
other
so
could switch.
yeah, so
Or
the
crazy.
physically you can see that it's just this pad, right? 3 pins over here.
Oh, okay.
but the left two pins are shorted physically. There's a wire in the middle.
Yeah.
So it's giving you some options. Like you can either use a razor blade to cut the wire in here to make a disconnection, or you can bridge these two pins, use a solder, a big solder joint to short these two pins. Just giving you more options after you get this board fabricated.
Yeah, it's just flexibility.
Yeah, you can cut it or solder it or join these two pins. Yeah. It seems a little bit unnecessary for our lab, but you just need to look at the connections, how this works, right? Okay. So batteries input goes through this path, go to the charging chip, chip's output, and you can see the input comes from where? USB, the two pins, remember? I showed you? These two guys. Okay, so these two guys from the USB directly 5 volts is charging up your battery, not the VCC. Is the VCC? No, it's not a VCC. It's the 5 volts from the USB. Okay? All right. So when the battery is being charged up, are we providing voltage to the system through the battery or no? Is the battery supplying power to the circuit or no? No. Because this guy goes to charging and charging connect to here. It's being charged up by the 5 volts, but there's nothing from the battery go to the rest of the system. Just let you guys know. So this charging chip is not the best one because there's another one which is able to do both. Okay? So when you're charging up the battery is also supplying power to the rest of the circuit as well at the same time. But this works for us. It's okay.
But I mean, when you have when you're charging the battery, that means that you have it plugged into the USB into the PIC board. Can't
Yes.
you use VCC from the PIC to still like do the functions you?
Yeah, you cannot change it because it's already physically
Yeah,
shorted to VCC.
Exactly. So since
Yeah.
it's shorted to
So
VCC,
it's still working, right?
Yeah. So
Yeah.
technically, you can charge the battery
Yeah.
and use VCC to run programs at the same time.
And you need the Dr. Carlson as well. Because he has to design this board for you, has both the USB and the VCC to connect to this daughter board, right? They have to happen at the same time.
Gotcha.
But otherwise, if you are just charging up this guy, but without the VCC, like all these female pattern pins, you won't be able to power up your system. Make sense? So this case also works, right? Okay, you guys need to know this because sometimes you plug in USB, you have this one switch to charging, switch to somewhere else. You just have to know what is really happening on the board. Okay, so for case 3, USB, VCC, battery, and unreg. I don't know what that means over here. Unregulated probably because it's bypassing this regulator, so that's why it's unregulated. So this chip is not being used. I don't know why, but anyway, it doesn't matter. It's just a wire, because you can see VNREG. It's bypassing this chip. It's not doing anything. So it's directly a wire here. Okay. Anyway, it's okay. So now let's see. What do we have? USB plugged in, right? What about the battery? Plug in. However, I'm not charging it. So I switch it to the right, right? To the right. So what's happening? Since VCC is through the USB, so the charging is over here. However, it's not doing anything. So the charging power reaches here and connect to here, but however the switch didn't select it. Okay? So it's not doing anything. So this charging circuit and VCC is not doing anything to the battery. Alright? So is this gonna work or no? What is this doing? The battery power comes here, goes to here, the switch to the bottom or to the right, goes to here, goes to here. So V and reg goes to where? Let's see. Goes to where? Shorted to VCC. Okay.
That goes there. And
It goes to here, okay? Then power up your MPU chip. Okay? So this also works. Alright. Now, if I do this, battery, VN rack. However, I don't connect to VCC, which means I unplug the daughter board from the PIC board. So there's no USB power VCC at all.
Yeah.
Let me show you. This, off the board. No USB, no VCC. Gone. Just these two guys. Plug in. All right. If I move it to charge, what's gonna happen?
Nothing.
Nothing. Because the battery goes to here, goes to charge, nothing. And you don't have VCC. So it should be off. Makes sense? It's off. All right. Next. If I move this one, battery comes here, and move it to VN rag, then battery power comes to here to the wire, bypassing this regulator, comes to here, and being shorted by this little connector to go to VCC. But we don't have VCC. What's happening? It's okay, just a label, right? We are not using the PIC board's VCC, but there's a common VCC node or metal on the board, on the daughter board. So this battery's voltage will reach that VCC node and power up every single thing on the board. Make sense? That's how that works. See the green light?
Yeah.
And it's unregulated, so we get like 3.7 instead of 3.3 from the LiPo.
It's not regulated at all. It's directly 3.7 volts. Would that be a problem?
If our board needs more power, do we just put two batteries in series?
Yeah, let's see what happens.
It's probably gonna damage this guy because this device, this thing now, it's receiving 3.7 volts. I believe the range is from maybe 3.2 volts to something like 4 volts. I don't know. But the MPU module is a 3.3 volts device, so definitely you don't want to put like 2 LiPo battery cells, which is giving like 7.4 volts to it. It's damaging. And the design is really cool. I was able to go through every single demo on this board for Lab14 and Lab15 as well. So you see Lab15 in lab. I haven't posted to Canvas yet, but I will do that probably later today. You'll see Lab15. I also deleted many questions. I only leave 2 left. So one is to calculate the angles. You just have to do this because this is the only place you can practice with the numbers. The numbers on the accelerometer. I'll cover that on Wednesday. Okay. But just let you guys know. Okay. So for in Lab15, only 2 questions. In Lab14, also 2 questions. And soldering.
We're doing it all in one day, right?
Yeah. No, I'm giving you 2 weeks. But the thing is, I'm expecting you guys finish Lab 14 and 15 in 1 week. But the demo will be the week after. So still have time. Let me show you the timeline here. What's that?
For people doing track 1,
Yes.
I was looking at Holston's lab,
Yeah.
the lab 15, where it has the defined project.
Yes.
And then the one you create, like using that.
Mhm.
Is that still a part of?
No. So for this one next week, just to be clear, it's only Lab 14 and Lab 15 in lab and lab itself, not the projects.
Yeah. No.
So the projects will be, demonstrations will be after Thanksgiving, right? So because you don't know what the demonstrations are on Lab 15, let me just show you on the on my website. I already did it, super simple. I did just one video, I think. Let's see. I think the operation has been stated on the website. Shouldn't be very difficult. So first of all, we should unplug this. Okay. And the battery is the only power source for this system. I'm still doing the Z. So before I unplug it, this was configured to record the Z axis of acceleration. So I want to maybe migrate it on the Z axis so I can differentiate this new data between the one as we convert it into the launcher because it was stationary. So basically it was just 1 G, right? So now I have to migrate it so I can tell the difference. So I know this new data is getting over. So I think the first step is you need to hold the top button and press reset. Okay, then press the middle button, show the bottom button, and press it. So record data. Migrate this a little bit. Okay, and then press top to stop. Okay, then plug it back in. So data was saved on SD card. Start new POTI session. Then split it out to the POTI.
So that supplies VCC to the PIC board?
Which one? It doesn't matter. I don't care about for this lab anymore. It's
How does this power the...
I unplug it, so it's not on VCC anymore. It's on the battery.
Yeah.
Why is that? Because for a second for here. So it smooths it out, right? And you copy and paste it to the Excel sheet and record it. That's it. And I think this is one of the tasks.
First line.
We did that in lab night.
Oh, yeah. Let's see. Take a look. So see, because if you don't vibrate it, it's gonna be a not flat because there's no noises. So it will be 1G, right? Because the gravity is 1G. However, if you move it back and forth by calculating using the register value, I'll show you on Wednesday, but it won't be 1G anymore. So 1G's value for the battery numbers is around like 8,600 something. But if you vibrate it, you are seeing like 14,000. So you can demonstrate that the Z-axis works. Okay, so you know that it works. That's it. That's everything you need to do for 14 and 15. Just demonstrate that your solder board works. So that's a 2-week task. It's really very reasonable. So I'm expecting you guys can finish everything. For example, soldering, you may not have the experience, but take the time this week on Thursday, try to finish up the soldering and the testing in Lab 14. Very simple, just testing the LEDs. I showed you the demonstration on the website. And Lab 15, if you have time, just get that done as well. However, the Lab 15 demos won't do until the Thursday after. So you can see the Thursday after will be track 1. It's going to be Lab 14 and 15 demos to the TAs. Okay? So solder.
Are we writing code for Lab 15?
For track 2?
For
No code at all. No code. Even for the project, I just figured that out. No code, even no code. So Lab 15, you collect the sample. You have to use this. It's called an autonomous module or mode, whatever that we call encoded. So you part it up using the battery, and have this one, have the SD card attached to this guy, and then you mount it to somewhere, whatever you want to experiment on, like vibration of the door, like a door counts or something. You count it, right? It collects data to the SD card. And eventually, you remove the SD card. You spool it out to the PuTTY and then to the Excel sheet and collect the data. Use Python or MATLAB to plot it and do a signal analysis. That's it for the listed projects for Lab 15. Make sense? Track 1, guys. That's all the tasks for you guys. But you have to have a meaningful project, which means you have to let me know what you're really doing, not just random vibration, right? You tell me these are the number of vibrations we have. If you look at the project, the 5 or 4 listed projects on Dr. Carlson's website, it says it's a door counter or like step counter or something, right? It has to be a meaningful project. It's super simple. So and reasonable, and it's awesome as well. So hope you guys can get it done in time, because I'm giving you guys a lot of time next week. So starting from Monday, Wednesday, we don't have lectures, and even this Friday. It's Friday, we don't have a lecture, so you guys will. So Thursday, for example, Thursday you'll start working on the Lab 14, right? If you didn't finish that soldering, so Friday come to the lab. I'll be there in my office area to help you out. Okay, so guarantee that by the end of Friday you should be able to get a functioning board. Okay, so for the following week you can start working on the demonstrations. No coding, demonstrations and data logging or the project itself doesn't matter. But you have 2 weeks, almost 2 weeks. Almost 10 days before the Thanksgiving to work on the project. Make sense? So Lab 15, the project won't do until the demonstration dates. I'll send out the schedule later. But now I think for this and next week it's very clear, right? And for track 2, you just work on your either Lab 14 or your course project. This Thursday and next Thursday, and next week as well. Okay, still have time to work on the exercise. Hopefully we can get it done today. Remember last time we talked about DSS? It's actually how the function generator works. So when you are trying to output different frequencies of the sound waves, you can use that low-pass filter and PWMs to generate these different frequencies of the sound waves. pulling you back to something like we covered 2 weeks ago. So do a quick review. This is wrong. This is wrong. Memory banks in there. Eventually, this ROM saves one period of sine wave values, and this is called lookup table. Because we are looking up values in this period and take them out to synthesize that points to a different frequencies of sine waves. Make sense? Can you still recall what we covered previously? All right. Now let's look at the questions. All right. So in order to, so for example, it's given here like every single 10 microseconds we take out 1 point, and then we can plot a sine wave exactly like this original frequency. Okay. So if we skip 2 points, or skip 1 point, or we take out points from this memory every 2 points, what's going to happen is we take out 1 point from the beginning, and the next point will, but the time is not changing, right? It's still like 10 microseconds. However, we are skipping this point, but taking these points out. So eventually, what's happening is we are having still the same frequency, still the same time intervals, but however, we're skipping the points. Keep doing that. Eventually, it will shrink the whole period to half the original period. So eventually, if you skip 1 point, we're taking 2 points every time. Eventually, the frequency will be doubled. Original frequency, what's the period of this original frequency? 10 microseconds for each time intervals, right? And it's given that we have how many points for the example? 64 entries. 64 points in total. So 64 intervals, 10 microseconds per interval. So what's the period of this sine wave? Okay? All right? So that's the period. 1 over it will be the frequency. Okay? If we skip 1 point or sample every 2 points, what's happening is we're doubling that frequency. So times 2. Okay, this number is called phase increment. And it won't work just by itself. It has to be implemented through another variable called phase accumulator. And now let's get to the I think that's in class exercise number 5, I think. Okay, number 2. Since we did this one last time, okay. If you're not here, probably open up my website and look at the notes. In class exercise number 5 and question number 2. Take a look at this code real quick. See if that makes sense. This is how we implement phase increment and phase accumulator. So first question, do you have this copy? See? Yeah. Okay. First question, take a look. First question is simple. It's an old question. How long is the timer 0 generated delay, assuming no prescaler, 16-bit timer 0 and 16 megahertz? Look at this part. How to calculate it?
2,000 counts at 16 counts a second.
That's the time delay, okay? Time delay. What is the time delay doing here? It's a while, right? If you don't press anything, it's gonna keep doing this. So which means it's generating the delay of incrementing that phase accumulator over here. So what is a phase accumulator? It's basically just starting from the beginning, you set a 0, and you keep incrementing that phase accumulator by adding a phase increment to it. And that's how that works. But let's see. How many entries you have? It's a similar problem. We have 64 entries, right? So here, it's a sine wave. You couldn't visualize it, but I'm telling you this is a sine wave. Okay? How many entries? Count it.
16.
Yeah, 16 entries, right? 16 entries. Given that we are incrementing that every whatever values, okay? So eventually we are getting the frequency, output frequency to be what? The phase increment divided by what? This value. Okay? That's a time delay. Times what?
16?
16. Very important stuff. So be on the exam, right? Just let you guys know. So that's the period of the sine wave, and that's the phase increment. Questions here first.
So what's the purpose of right shifting the phase?
We'll get there. What's that? What's the question over there?
Oh, it's different. Sorry, I didn't know where the phase increment was.
Okay, we'll talk about that. What's that?
What question is this answering?
It's answering the second question right now. What's the frequency resolution of the DDS? But you have to know this first.
So is the F out the frequency resolution?
Frequency resolution will be the phase increment divided by the period. So which means every single increment, how much hertz you are changing. Make sense? That's the frequency. Hmm?
Not really.
So it's just like because you are changing the phase increment to change the frequency output. Because of this.
The frequency output is what we're looking for?
Hmm?
The frequency output is what we're looking for?
Yes. For now, yes. Okay. Okay. So now let's look at this part. If this makes sense, right? It probably won't work if we just look at the numbers. Okay. You see, because we want to increase the speed of the microcontroller, we don't want to use float points or fractional numbers. So it's you trying to use that integer, okay? If you use integer, it's difficult to create a fractional number of phase increment, like 1.2, 0.5, 0.2, something like that, okay? So the strategy over here is just creating, like, for example, use 10. That's okay, because 10 is being divided by what?
4 times. So
Yeah, right shift by 4 is divided by what? 2 to the 4th, right? So it's basically the phase increment here is what? But we didn't use the floating point, or we didn't use the fixed point, fractional number. We just use the integer, but eventually this still works.
because we're dealing with integers, wouldn't index just always be 0 then?
No, because the phase accumulator will eventually,
Oh, it'll
the
eventually
effect,
pass 0.
yeah, will the fractional part of the numbers will eventually, the effect will manifest into the phase accumulator. And why we have to do this? Let me show you this spreadsheet really quick. It doesn't make sense in your brain because you cannot make like 3 columns in your brain, right? Let's see this. Index, okay? For example, index is basically the number of the index for the sine wave. Doesn't matter, you are incrementing by 10 each time, okay? Why? Because if you look at this, one, how is this index being used? So index is basically the phase accumulator, right? And then you use that shifted phase accumulator as the index, you're taking out points from the sine wave array. Okay?
So for the first 2 cycles, it'll be 128. So
Let's take a look.
128, and then it'll
Yeah.
go to the next one because it'll round up.
Take a look. Yeah, exactly. That's the idea here. But let's take a look. So these are index. Okay, so definitely you don't want to skip by 10, right? So that's why you shift it by 4, which is divided by 16. If you see this column is divided by 16, so see what the integers are. 0, 0, 1, 1, 2, 3, 3, 4. That's how that works eventually. However, if you divide by 4, you see what are the index. 0, 2, 5, 7 is too much, right? You want to have 16 entries.
Yeah.
Okay? But if you divide it by 16, only take out the integers. You don't need to generate floating point numbers or fractional numbers in your pick. which takes a lot of computational resource. So you can directly use integers and taking out the integer part of the fractional numbers, eventually use them as index. So eventually the fractional parts, okay, see the fractional parts, even though we didn't use them, eventually they accumulate and have an effect onto the integers. What's that?
This, as soon as you go to 16, it's gonna go past the number of. Yeah, I mean you're gonna.
Let's take a look at the code, see how that works
The
eventually.
code doesn't account for that at all. Just wait for you to press the button. So you're gonna end up trying to access a part of the memory you don't have access to.
Let me see how that works, how that flows back. I probably didn't include it into this piece of code. There might be somewhere like you can check the index. This is not overflowing over there.
Oh, I guess.
Mhm.
No, never mind.
It doesn't matter though. I mean,
Well, because phase accumulator is only an 8-bit integer, so it's only going to go up to 255.
oh yeah,
So
yeah.
you're no, yeah. It would just overflow. And then
Oh yeah, because 255 divided by 16 is 16, right?
Yeah.
Yeah, yeah. So it will come back eventually.
Oh, okay. Well.
All right. So now, what's frequency resolution, which answers this question? So you'll get 1 point. 1 point for each. All right. So what's the frequency resolution? To answer this question, what's the frequency resolution? Answer the first question first. What's the phase increment? Actually.
Oh.
Right? That's 10 shifted by 4. That's the phase increment. So what's the period? Delta F, right? What's the period? This thing times what? 16. Good. Good catch.
10 over 16. So it's like 10 over 16 times 16 times 25.
Okay, that's what I did. So we didn't do the DDS lab, but eventually in the lab, I was looking at the solutions on the website. It's showing a 31.25 hertz. I think the calculation was wrong over there, or they probably used the 1 for the phase increment over here in the code. Doesn't matter, but I think this is correct. So you are done with this. I'll have 1 minute left, and probably we have to spend some time on Wednesday to figure out this one in class number 4. But you can turn this in today. In class number 5, turn it in today. Okay? So turn in the in class number 4 on Wednesday. So we have another lecture on Wednesday.
Professor Lee, so just real quick clarification.
Yeah.
The phase resolution is the smallest frequency for which you can change.
Changed
Okay, so like
by
you can
by
only-
incrementing that
Yeah,
phase.
I start at 0 hertz, go to 3 to 12 hertz, go to 600 whatever hertz.
Yeah.
900, so on and so forth.
Yeah, if you add. Oh, actually you are right. Depending on how you increment it.
Oh,
So that's why it's a 31 because it's adding 1 to it. If you add a 10 to it, then it's gonna be 312.
1 over 16.
Yeah. 1 over 16 if you add a 1 to it. Because the integer, so you cannot add like 0.1, so 1 will be the smallest number.
But that makes sense.
Makes sense, yes.
Professor,
Cool. What's that?
I have a question. Because when I